Hey guys, today we're going to introduce the next unit, which is that of gases. So here I've got a balloon. Now, this balloon is currently not filled with anything, right? So it's empty. But what is going to happen when I start adding a gas is that all of a sudden this balloon now has changed. You can see the balloon now has something we call volume. So the volume of this balloon increased because I've added a gas inside. Now you can't see that gas because the second I release the balloon, you didn't see anything come out. So let's start by talking about what is a gas, and then we're going to start discussing why that gas made this balloon inflate the way it did. So we're going to start by talking about some of the fundamental properties of gases. So the first property we're going to discuss is that of temperature. Now we've talked about temperature already this year, but we're going to go ahead and have temperature in our back pocket as average kinetic energy of molecules. So the temperature of any gas represents the average kinetic energy of all the molecules of that gas that are present. Remember, temperature is by itself a measure of average kinetic energy. So not every molecule of gas will have the same kinetic energy, but if you take all of the gas in a container together, the temperature represents the average kinetic energy of all of those molecules of gas is 1. The next property we're going to look at is that of pressure. Now, pressure is kind of an abstract thought, so let's go ahead and give it some tangible definitions. First of all, molecules of gas are just that. They're molecules, they're things. They have mass, they take up space, and because of that, when they run into something, they impart a force. This is like if I were to run headlong into a wall. If I ran into the wall, I'd exert a force. Now, the force I'm exerting is a pressure. Molecules are exerting the same force on any wall of any container that they're in. So for this balloon, right now, there is gas all around it of the atmosphere. That's exerting a pressure inward. That's keeping this balloon deflated. There's nothing inside to push it back out. Now, the second I add gas to the balloon, now all of a sudden I've created a force inside pushing out. So inside of this balloon, there is a pressure being exerted by the gas inside. That pressure is because the molecules of gas are colliding with the walls of this balloon and pushing the balloon outward. Now, pressure in chemistry this year can be measured in one of many different units, but the most common units you're going to see are that of atmospheres, millimeters of mercury, or torr. These are the three most common types of units for pressure measurements, but there are also things that you could see like kilopascals. Most likely you're going to see the first three though. Now, in any case, as pressure increases, that's telling you that the force exerted by the molecules on the sides of the container or on whatever's measuring the pressure have also increased. Higher pressure, greater force. Now, volume of a gas is abstract again. It's hard to visualize because gases, well, they are hard to visualize. So let's think about this balloon. Now, this balloon has currently a volume, which we'll go ahead and say is 0. All right, it's not filled with any air at all. Now, the second I start inflating the balloon, its volume increases. Now, the cool thing about this is that when I look at a balloon like this and its volume has increased, I can measure that volume. Now, this is a flexible container. A flexible container is one whose volume can change over time as other variables have changed. But you also might end up with rigid containers. Rigid containers are those containers whose volumes cannot change. The cool thing about this is a gas, any gas, is going to expand completely to fill whatever container it is in all the way. So when we look at a volume of a gas, we simply need to look for the volume of the container in which that gas is held. The next property we're going to look at is that of the quantity, the amount of a gas. And the way we're going to quantify that in this course is going to be using the number of moles of gas present in a container. Now in this unit, to simplify the math, we're going to make an assumption that every gas that we deal with is going to behave in what we call the ideal way. In order to go ahead and make this assumption, it's actually made up of several different assumptions. So let's go through those real quick. The first assumption we have to make is that all molecules of gas move in straight and random lines. So in other words, a molecule of gas doesn't know where it's going. It's just going to bounce around randomly. Now that assumption actually is fairly true, right? Molecules of gas, when they're moving around, they do move somewhat randomly and in fairly straight lines. So that's actually not a hard assumption to make, and it stays relatively valid. The second assumption that we're going to make is the fact that when a molecule of gas collides with anything, whether it be a wall, a pressure sensor, or another molecule, the collision between that molecule and the other thing is perfectly elastic. Now, elastic means no energy is lost. In other words, the energy with which a molecule had going into the collision is the exact same as the energy that a molecule has leaving the collision. That is not necessarily true, but we're going to go ahead and make that assumption to assume ideal nature. The third assumption we're going to make is that the molecules themselves, they don't interact with each other at all. So there are no reactions, there are no interactions in terms of whether they are going to attract each other or repel each other, no interactions at all. That's an assumption we are going to make that is oftentimes invalid, but mathematically speaking, oftentimes we are going to make that assumption in order to make the math easier. The fourth assumption we're going to make is that the molecules of gas have no volume themselves. So if you think about the room that I'm in right now, the room I'm in has volume. There's gas filling this room. But I'm also in this room. I'm taking up space that otherwise would have been taken up by a gas. So by my presence in the room, I'm actually displacing some gas. We're going to go ahead and make the assumption that molecules of gas don't displace any of their own volume, as it were. So we'll go ahead and assume that any molecule of gas is just a single point source of this force that we call pressure. Now I want to go ahead and explore, using kinetic molecular theory, the relationships between pressure and volume, pressure and temperature, and pressure and number of moles. So what we're going to do is, using a visual representation, a particle diagram, we're going to go ahead and try to visualize what is going on in each of these relationships. In the future, we're going to quantify this. So we're just going to take a qualitative look at this right now. So let's go ahead and do some visualizations to be able to actually see how a gas might behave in a container. Now, particle diagrams are going to be very common in this unit. The reason we use particle diagrams is to visualize the molecules that make up a gas. First thing you need to be able to do in any particle diagram is represent a gas properly. In order to do this, we show the molecules separate and moving. Now, this represents a gas. The molecules are seemingly randomly distributed throughout the container. They are going to fill the container. So if my container was twice as big, it would still have the same randomness to it. Molecules moving, that means I'm showing this line of movement, because again, the idea is if a molecule has energy, it's going to be moving. This is unlike in a solid where the molecules simply vibrate. In a gas, they're actually moving from one place to another. Now, one thing to be aware of is that as these molecules are moving, the things they're going to collide with. First thing that they can collide with would be a wall. Now, that collision right there, you can see as a molecule comes in, it strikes the wall and it returns back out. That collision exerts a force on the wall. That force is pressure. The pressure that's exerted on the wall is going to push this wall out. Now, in this container, I could have two properties. I could have a rigid container, or I could have a flexible container. Now, a rigid container like this, it doesn't matter the force pushing out because the volume of the container stays constant. So if I were to say a rigid container, I'd be talking about a container with constant volume. Additionally, when I'm looking at a container, it can have another property. The property of another container could be flexible and isobaric, or same pressure. Isobaric containers would be represented by a balloon. No matter how big I inflate the balloon, we assume the pressure inside is the same as the pressure outside. Why? Well, because as you inflate a balloon, the pressure inside is going to continue to push it out until the pressure inside and outside are, well, equal. So, A balloon would represent a vessel or a container with constant pressure. The third thing we might see is a sealed container. Now, a sealed container is exactly what it sounds like, a container that lets nothing in or out. A sealed container, once you start with a certain amount of gas present, it's the number of moles of gas that stays as it is from the beginning. Okay? So, we can see the properties of a container. We can be told the properties of a container. Now let's look at the properties of gases in those containers. Now, kinetic molecular theory is going to tell us how each of these properties, temperature, pressure, volume, and number of moles, are going to relate to each other if you're going to be starting to change some of the variables. So let's change the volume. I'm going to start with a container of gas. It's got 4 molecules of gas. All right, we'll call it 4 moles of gas for ease. And I'm going to increase the volume of the container. So let's think about what this might do to the pressure. Well, the pressure of this container is going to be predicated based on the number of collisions that the molecules have with the wall and the force with which those molecules are colliding with the wall. Now, by increasing the volume, I'm not actually going to be changing the kinetic energy of the molecules directly. Right? Let's assume we have constant temperature. So what we're going to look at now is if we had an increase in the volume, what happens to the sheer number of collisions with the wall? Each collision exerts a force. That force can be added together and quantified as the total pressure in the container. Well, if I increase the volume, each molecule has more distance to travel before it hits the wall of the container. That tells me that there are going to be fewer collisions. Fewer collisions with the walls of the container. That means the total force exerted on the container is going to be less. So when we look at this, if we think about it in terms of kinetic molecular theory, the reason that the volume and the pressure are related is because as volume changes, the number of collisions change. All right, so in this case, as the volume increases, the number of collisions becomes less, and therefore the pressure is decreased. So now let's think about how changing the temperature impacts the pressure. Now, again, changing temperature changes the property of kinetic energy. So as you increase the temperature, you're increasing the average kinetic energy of the molecules. What this does is 2 things. Number 1, it makes the molecules move faster. So as you increase the temperature, the molecules are going to move faster around the container. The second thing that's going to happen is that as you increase the temperature, the molecules, when they hit something, are going to hit it with greater force. Think about this in terms of you walking into someone or you running into someone. As you move faster, you exert a greater force, which means as we increase the temperature of the molecules, they move faster. They collide more frequently with the walls. That adds to a greater pressure, and when they collide with the walls, they do so with greater force. That also increases the pressure, which means as you increase the temperature, you're also increasing the pressure based on the magnitude and number of collisions. The final relationship we're going to look at here is how changing the number of moles might impact the pressure. So when it comes to changing moles, what we're doing is we're simply adding, in this case, from left to right, more moles of gas, more molecules of gas. Well, as you increase the number of molecules, you're actually going to increase the number of collisions that are existing with the wall. Again, molecules are moving randomly. So the more molecules there are, the more of them are going to collide with the wall. That is going to increase the pressure due to the increased number of collisions. Again, if we are holding our temperature the same, each molecule has the same kinetic energy on average as it did here. But because we simply have more molecules, the pressure increases due to the increased number and frequency of collisions that are occurring. So that wraps up today's video. Let's do a quick recap. Today we discussed the 4 major properties of gases that we're going to explore in this unit. We talked about the pressure, the volume, the temperature, and the number of moles. We also discussed the assumptions we need to make in order to be able to treat any gas as if it behaves in an ideal way. In the future, we're going to start discussing those relationships more explicitly. So we're going to quantify the relationships between pressure, volume, number of moles, and temperature. And we're going to look at gases that may or may not behave in an ideal manner. In this video, I want you to walk away with a conceptual understanding. Do you understand that gases are things made of molecules like you and I? And as things, they can exert forces, and they have properties that can be quantified. I'd like to thank Sam Nyan for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.